We're now going to move away from talking about the fundamental forces, or those forces that are acting at the particle level, and talk more about common forces, the kind of forces that we see in our everyday lives. And one of the first ones that's good to talk about is gravity, because gravity is actually something that fits into both categories. It's a fundamental force, but also one that we see on larger scales in our everyday lives a lot. And so before we talk too much about the force of gravity, we also need to talk about a new concept of weight. And so weight is something that you've probably heard a lot before, but you always thought of it as meaning the same thing as mass. But there is a difference. So everything has a specific mass, regardless of where you're located anywhere in the universe. It's kind of a measure of how much stuff is inside of an object, related to how densely packed all the material is in an object and how much space it takes up, your density and your volume. That's your mass. But your weight in physics is actually defined as the force of gravity that's acting on that mass. So when you're standing on a bathroom scale, for example, even though it's making some conversions and giving you a reading in kilograms, what it's actually doing is measuring how much force is pulling down on the scale, how much force is squeezing down on the scale, and then converting to kilograms for you. But your actual weight should be measured in newtons, because it's a force and not kilograms. So if we want to look more specifically at how we calculate the force of gravity, we can start by using a fairly simple equation in most cases. So our equation says that Fg, or the force of gravity, so that's F for force and the subscript g for gravity, is just mass multiplied by a new variable, g. And g is actually an acceleration, but we give it a special letter g instead of using a, because it's a really special acceleration. It's the acceleration due to gravity. But it's still measured in meters per second squared because it is a measure of acceleration. This allows us to get a little bit of an understanding of what a newton really is. Because as we see in the definition, force is measured in newtons. So if we just do a little bit of unit analysis, we can think about what a newton really means. We get newtons in our answer, and we do that by taking a mass unit. Specifically, when we do these calculations, we will always make sure we do it in kilograms. So if you have your mass in grams, just convert it. And then we multiply by an acceleration unit, meters per second squared. So what that means is that we have one overall unit called a kilogram meter per second squared, which literally means the two units multiplied together. And that little dot in between just means multiplication. And so what this literally means is that if you apply 1 newton of force, it could also be called 1 kilogram meter per second squared of force. And what that definition actually means is that 1 newton would be the amount of force required to accelerate a 1 kilogram object at 1 meter per second squared. And again, in general, we use the symbol g to represent that acceleration. And when it's just here on Earth, we'll use just a g all on its own. But the amount of gravity you feel is actually different on different planets. So if we ever talk about the gravity on a different planet, like, say, the moon, we'll use a little subscript moon. So g moon for that, or if it's on Venus, we'll talk about g Venus in that way. We also just need to remember that gravity always acts straight down. And that's because it's always trying to pull you towards the center of the planet. So regardless of where you are on the surface of that spherical planet, or roughly spherical planet, it's always trying to pull you straight down towards the center. So now we can be a little bit more mathematical with this and see how we would actually solve for a force of gravity. In this case, we know the weight of a we're trying to find the weight of a 45.2 kilogram dog. So if I just asked you that question before ever starting this note, you would have thought it was kind of a strange question. You would have said the weight of the dog is 45.2 kilograms. But now we know that that's actually not the weight of the dog, that's the mass of the dog. So that's actually the first given quantity that we can write. The mass is 45.2 kilograms. We also know g. And for our purposes, like we've been doing so far earlier in our kinematics unit as well, we're going to call it 9.8 meters per second squared. Now that 9.8 value is actually approximate. depending on where you are on the Earth, there are actually slightly different values for that gravitational effect that you'll feel. But we always round to an average of about 9.8. And in this course, I want you to just continue to use 9.8 unless it's otherwise stated. You can also consider that to be a constant value or a given quantity that won't affect our significant digits in any way. We're asked to find the weight, and of course we don't want to have to write out that whole word weight every time, so we need to think of a variable that represents it. But instead of using W or something like that, we need to remember that weight is actually force of gravity. So really I should use the variable Fg is really what I'm trying to find. That is my required value. So if I divide up my space to give myself some room to work, now I can use the formula that Fg is equal to mg, substitute in the things that I know, 45.2 kilograms, 9.8 meters per second squared. When I put that all in, I get about 442.96, but I'm then going to round that off. And this is why I mentioned the significant digits piece. I'm only going to consider the kilograms part in my significant digits, which the 45.2 had 3 significant digits. So I'm going to round this to 443, and the answer must be in newtons, because it's a force. So again, the 9.8 meters per second squared you can take to be a constant that's given to you, and so it won't affect your final number of sig digs. In general, always make sure that you're writing a therefore statement in your notes and on all future tests and assignments, but I'm going to skip over that piece and move to the next question now. If we've got a truck that has a weight of 4905 newtons, we want to find its mass. And so once again, the reason why the truck has its weight stated in newtons is because the weight is really its force of gravity. So that's one of our given quantities that we know. We actually know the force of gravity, in this case that's acting on this truck, is 4905 newtons. Once again, we still know that G is 9.8 meters per second squared, and in this case it's mass that we're actually looking for. So we start with our original formula that we know, that Fg equals mg. And we could actually substitute in the things we know right away and then rearrange the formula from there. But we can also just rearrange it while it's still in its variable form. So we could say something like mass is equal to force of gravity divided by g, which is what we get if we were just to divide both sides of that equation by g. So more specifically, that's 4905 newtons divided by 9.8 meters per second squared. When we do that, we get about 500.51, which I'm then going to round off to 500.5 kilograms. And why 500.5? Because that has 4 significant digits in it, and 4905 had 4 significant digits in it, and we don't worry about the 9.8 along the way. Once again, always make sure you're including a therefore statement to say what the final mass of the truck would be. Example 3 is just a common question that we often ask related to gravity that I just want you to think a little bit about, and we'll talk about in class in more detail. So think about what would fall faster, a bowling ball or an apple, and we'll take that up in class. For now, though, we're going to move on and talk about the next most important common force that we deal with in our everyday lives, and it's called the normal force. The normal force is a contact force, and it's the force that is always pushing back from a surface every time we push up against a surface. So, for example, in the first picture you see a book sitting on a table. And we know that that table, or that book, for example, isn't moving at all. And that's despite the fact that there is a strong force of gravity trying to pull it down. It feels some weight. The force of gravity is pulling down. So why isn't it moving down as it's being pulled? We just saw in our first note that forces should cause things to accelerate. Well, it will be stopped from moving if there is some equal amount of force pushing back up in the exact opposite direction to counteract it. And specifically, that force that's pushing back up is a force that's coming from the table that's stopping it from going through that surface. And in our everyday language, we call that the normal force. But it doesn't always have to be a force that points straight up. It just happened to be in that first case because it was working against gravity that was pulling straight down. But the key is that those two forces, the gravity and the normal force, were both equal in magnitude, same amount of force, but opposite in direction. And the same is true even if the normal force doesn't go vertically. So for example, in the second one here, if we push with our finger against a wall in that direction, obviously your finger will stop. It's not going to keep moving through the wall. So there must be some balanced force from the wall that's equal in size to your pushing force that's pushing back from the wall against you. So you can clearly see in this case that green normal force line is not going vertically at all. It's actually pushing back horizontally because your force that you're pushing into the wall with is horizontal. So the normal force will only ever point in a direction that opposes whatever force is trying to pull it through a surface. Once again, the strength of this green force that's pushing back must be equal to the blue force that we're pushing with. They're equal in magnitude, but just opposite in direction. And that helps to cancel out those two forces and stop the object from moving right through that surface completely. So we can now see what kinds of problems we can solve using this concept of normal force, alongside the fact that we also know how to calculate gravitational force if we need to. So example 4's got a 654 kilogram horse just standing on the ground. And we're going to draw all of the forces acting on the horse. And the key is that we need to just draw what directions the forces are going in. Really doesn't matter what our horse looks like. So if you want to draw a very beautiful artistic drawing of a horse, that is up to you. I have terrible art skills, so my horse is going to look a little bit like this. In fact, I'm just going to draw a box to represent the horse. You could have just drawn a circle or a large dot to represent the horse, and that's totally fine as well. It really doesn't matter what the horse looks like. What matters is what directions the forces are pointing in from that horse. So I'm going to just draw a dot right in the center, and that's kind of representing the center of mass of the horse, where all of the forces are working. And we know that in this case, it's going to feel some gravitational force pulling it down. And so I'm going to label this force vector with an FG. And I also know, though, if it's not moving through the ground, despite all that force pulling it down, there must be some force counteracting that. And so that's where this new normal force comes in, which I'll label Fn. And for now, I'm okay if you don't put the vector arrows on top of those force symbols, even though in reality force is a vector. You can see in this note, we're really actually just focusing on the amount of force involved. Specifically, if I also want you to state the full direction or the full vector, you could just use your diagram to figure out what direction it points in. But we're more concerned right now of just figuring out magnitudes. So those are our simple forces mapped out for the horse. We can also add a little bit more detail to this diagram, though. In math, whenever you've got two lines that are drawn on a page that you're trying to indicate are equal in length, we often use little dash marks, like so. And so I'm going to insert those little dash marks in, and they just mean that even though I haven't perfectly drawn this using my measurement skills, those are supposed to be indicated to be the same length. And so they should be the same magnitude, but opposite in direction, which is why the horse is just standing stationary on the ground. Now that we know all this, though, we can use that in order to figure out how much normal force is acting on this horse. So just to state our givens below, as we work on part B, we know that the mass is 654 kilograms. It's good to remind ourselves that we also know G in case we need to do anything related to gravity. And in the end, though, we're not trying to find force of gravity. We are trying to find normal force, Fn is what we'll call it. So we're trying to find Fn, but I haven't given you a formula for Fn. And that's because there is no specific formula for normal force. There's no specific amount that it will always be equal to. It's going to equal however much it has to balance out whatever force is pulling through a surface. So, for example, in this case, it's the gravitational force that's trying to pull the horse through the ground. And so normal force is just going to be exactly enough to completely equal the gravitational force. So in this case, we can make this simple statement that Fn is equal to Fg. That's not always true, but that happens to be true in this particular case. And just be careful of that, because it's going to happen a lot where normal force will often be the exact opposite force to gravity, and they will cancel each other out. But if we're ever standing on angled ground, like on a ramp, or if there are any other forces pushing down or pulling up, then this statement here will not be true anymore. It just happens to be true in this case because we're on horizontal ground and there's nothing else pushing down or pulling up. So our normal force will be equal to our gravitational force, which means we can use our formula for gravity to help us solve from there. So I can plug in what I know, 654 kilograms times 9.8 meters per second squared. And when I do that, I get 6409.2, or approximately, well, in this case, this should have 3 sig digs in it, so that would be approximately 6,410. And that is in newtons, because once again, it's a normal force. It's an amount of force. Of course, on a test or an assignment, you'd also just write a final therefore statement to say that therefore, the normal force acting on the horse is 6,410 newtons, approximately. The final example that involves the block sitting on a ramp is a bit more challenging, and we're going to take that one up in class. And of course, we'll also talk about the question earlier in the note about the bowling ball and the apple.